Hi everyone, my name is Nalini Venkatasubramanian. I'm a professor of computer science at the University of California, Irvine, and I've been here for some 20 odd years. Prior to that, I have some industry experience, and I guess that has influenced quite a bit of how I think about designing systems and how I think about deploying systems as well. And so, as you'll see today on this brief talk, a lot of our work has been with real world partners and systems and actual users and communities and agencies. And I have to give a shout out to them. Deeply thankful for their engagement. As Teresa mentioned earlier, there's a civic engagement project, a civic innovation project that I'll briefly talk about at the end. So, essentially, today's talk is about data-driven smart spaces and how you build resilience and what the need for resilience in these kinds of infrastructures is. So what are smart spaces? So in many ways, one can think of smart spaces as physical infrastructure, built infrastructure, buildings, bridges, transportation networks, water infrastructures that are instrumented with a variety of devices for sensing, actuation, etc. And essentially, the way I do a lot of work on software systems, and the way I think about it, these systems or these devices or these components essentially take me through this loop where I'm able to monitor what's going on in that space and observe. Hello? Okay. That I'm able to observe what's going on, analyze to create awareness, and essentially, decision makers or in an automated way, actions are taken. So this observe, analyze, adapt, and act loop is something that plays out in a variety of situations. And over the years, actually over the last 20 years or so, we have built many different smart spaces in a variety of projects, and many of them with a resilience focus. And the idea here is that, in a day-to-day, this is a picture of the UCI campus with a variety of sensors that we did for one of our early projects on emergency response. On a regular day, you would use this for things like, surveillance of what's happening in the space, monitoring, etc. However, this very framework, in some sense, morphs into providing better situational awareness. For example, if there's a fire in the building or there's some kind of an active shooter on campus, the smart infrastructure should, and it's always not that easy, essentially transform itself into providing situation awareness for dispatch, for the fire incident commander, for perhaps folks who are coming in to resolve the situation. So essentially, at the end of the day, what these smart spaces do for us is create a digital representation of an evolving world. The fashionable term these days is digital twin. And what you're really trying to do there is to be able to capture people, you're able to capture spaces, you're able to capture events, and essentially distill that into better awareness for more informed actions. So over the years, and I'll rush through some of these, we've built a variety of smart spaces, as I told you. One of them was ResponseSphere, as a campus-wide environment to over about a fourth of our campus to essentially monitor and instrument disaster drills. Well, we had a lot of emergency response projects, and you can't exactly test by creating fires or creating earthquakes or emergencies, so we have to emulate them and test our technology. So this was an NSF-funded research infrastructure project that allowed us to test with agencies such as the Orange County Fire Authority and Los Angeles Emergency Preparedness Department. We had another FEMA project where the idea here is you instrument a space with essentially the goal is to be able to keep the firefighters safe. It turns out that when firefighters enter buildings, in order to, or any kind of situation, many of them experience, health issues. It could be afterwards. It could be, a lot of blood carbon monoxide inhalation during the different firefighting practices. Maybe even many of them experience, very severe cardiac issues because they are in the throes of responding to that event. And so here, by instrumenting the firefighter and instrumenting the space, with a variety of sensors, essentially we're able to create this kind of reliable, timely situation awareness. And there's another one where we're able to lift information out of speech and radio, used again in fire as well as in sort of defense applications, to be able to extract information and extract situation awareness from speech data. More recently, I think in the last, since 2015, 2013 to 15 or so, we started this other effort, which I'll describe, where we started looking at cheap sensors, things you get off the internet, your $10 sensor that you buy off the internet. And we instrumented a senior housing facility, which I'll talk about. This is the SCALE project in Montgomery County, Maryland. This was a NIST White House Smart America project. And today, you see a lot of things with the Global Cities Challenge. So this was sort of the precursor to that. So, and out of all of these projects, I won't talk about these, but there were several software artifacts that we had developed and deployed to improve resilience. Essentially, the key thing here is that, in many of these situations, you're embedding it in a space where there are humans conducting actions with certain processes in mind. And so part of how you infuse technology into an ongoing process without actually, dramatically changing the process was sort of the name of the game. I'll describe in the very short time we have, very briefly, 3 different projects in this kind of smart community space that kind of embodied what I call this observe, analyze, adapt principle. One of them is the SCALE project, which is about a smart home. One of them, as we'll extend later, we'll talk about, is a DARPA project that is on looking at smart buildings and looking at privacy of developing sort of very interesting services that residents and external folks can have out of smart buildings, but with privacy in mind. And more recently, I'll describe our Civic Innovation Challenge project, which is the project which specifically focuses on one community, which is the older adult community, and how to enable disaster resilience in these kinds of settings. So the Smart America project was really interesting. It kind of is the way I think about it, it's about democratizing IoT, democratizing sensing and making things smart in a way that doesn't require very high technology know-how or is very expensive. So part of the idea is, how do we extend this Internet of Things and services from the Internet of Things, create smart spaces for everyone. So in this case, think of the picture I want you to have in mind is an older adult at home on a wheelchair, living by themselves. And what we're trying to do is to instrument the home, perhaps instrument the older adult themselves, to be able to detect things such as, hey, the gas stove, there's a fire on the gas stove, or there's a gas leak, you forgot to turn the stove off. Or maybe there was a fall in the house and the person is all alone. And so being able to design platforms, end-to-end platforms for these kinds of systems using everyday sensors that we get out is a huge interoperability and integration challenge. And so we started out by this as an interoperability exercise where we brought together companies. Actually, you see 6 of them here. The second version of this had 26 companies. And the idea was that data from these homes would go through some kind of long-range, low-power wireless network that the county provided. Data would be sent to a cloud-based public safety awareness system. In this case, it was operated by IBM. And because these devices and sensors are your cheap, off-the-shelf internet sensors, they don't always work very well. So, the issue of accuracy of the analytics, so the devices are not very accurate. The analytics that you perform on top of it is not very accurate either. So here's where we decided to bring a human in the loop. So there was if you detected a problem in the house, a phone call would go out through a service called Twilio to the older adult, and they would be responding and saying, hey, I don't need help, I just, burnt my toast. Or they would actually say, yes, I do, or not respond, in which case, somebody would be there on the way for help. And this whole loop, in some sense, as an interoperability exercise, was cobbled up together with off-the-shelf devices and demonstrated in a matter of 6 months. But after a few, as we started looking more deeply, the real interesting work from research point of view came after that, which is um, devices started to fail. So these internet sensors that you bought, after a couple of months, they didn't work as well. Second, the devices that you put in the home of these adults, there's this issue of being able to monitor, critical situations 24/7. So if I take one of the places we extended this to was a senior living community, and here you're trying to strike a balance between safety and independence, right? So you want people to live independently, you want them to be independent for as long as possible, but you also want to create a safe environment. And this is what smart homes or smart spaces in this setting have to do. These smart spaces, unfortunately, and we'll talk about privacy in the next project as well, require perpetual monitoring. It's not enough for me to say, I will monitor if you fall down at this very location between 5 and 7. You have to be on all the time. And that creates an interesting issue. So we developed a variety of fall applications. One of the key issues we focused on was falls. Because a lot of older adults do fall, and there are several. It's a very big public healthcare challenge, and many such adults live alone. And so this kind of 24/7 capture, apart from being a privacy hassle, has other problems. You can't not do it for a certain amount of time. So there are several approaches. Let's take fall detection as an example because it's one we worked on. There are mobile phone apps, and there are smartwatch apps. But the issue with a lot of these things is we found out that you know energy was a big issue. So you have to keep charging the phone. If your phone is not on you, or if your phone is out of charge, you're out of luck. We moved on to other kinds of things such as wearable tags and sensors, and today that technology is improving. But even so, you have to change batteries every now and then, charge your devices. And for someone who's living alone on a wheelchair, this can tend to be an issue. So, providing reliable information in these kinds of settings requires not just these kinds of device-based technologies, but also ambient solutions. So with that in mind, we developed technologies such as a smart carpet, smart mat, and a bunch of other technologies that allowed us to fuse this information together, monitor what's going on in the space, analyze this information for activity recognition, which is persons in the kitchen, or persons just is walking around, or person is sleeping, or person may have fallen down. And this kind of activity recognition itself is a challenge, as many of you on this call will attest to. And doing this accurately, doing this especially in a privacy preserving way, is hard. And so that was sort of what this effort was about. One of the things we focused on was, how do we make sure the lifetime of these battery operated devices and the amount of energy consumption, if I put lots of sensors and devices all around the home, they have to be powered somehow. And so then that starts to be less sustainable if you think about it. So we were able to use intelligent triggering techniques and intelligent combinations of sensor fusion methods, and essentially save energy, extend battery capacity, and while not actually sacrificing on accuracy. So if there was a critical event, you still detected it, and in time. And that was sort of the goal behind that work. And we're not the only ones doing this kind of work. There are quite a few others. Here's an older example from the CASUS project at Washington State. Again, the idea was to be able to use AI-based data-driven techniques to be able to trigger, detect when there's an anomalous situation and trigger that. Today in our projects, we're also using acoustic sensing. If a person falls, there's probably going to be some noise around. And if I can get some ambient noise information and couple that together, I can get better accuracy. So as I expand this kind of smart home, as we do this to other kinds of applications, medication management, gait monitoring, there's a whole host of challenges. Each of these devices, and a big one is interoperability, which is I have lots of devices. Which one do I use? When? How do I send the data? each of them may be using different, some are Bluetooth, some are, low power wireless, some are Wi-Fi, some have their own network and their own, stack solutions. How do we deal with this is a cross-layer challenge that requires sort of an interdisciplinary approach to be able to understand how do we do this in general. So I can give you a fall detection application, but in a smart home, you may not be falling all the time. And so you may need other things. So with that in mind, that's sort of, I'll leave you at that, and there's happy to follow up. I'm going to move on to a second slightly larger project, which is not a home, but a building. And this happened to be our computer science building at UC Irvine. This was a project which essentially looked at IoT, but also brought in this aspect of privacy, and essentially into exploiting IoT with building management systems, but in a privacy preserving manner. And thus, I have to give a shout out to my collaborators here. We have had a huge team and a huge effort over the years. So I'll give you a quick overview of that project, and my slide doesn't want to go. So many folks on this call are very familiar with building management systems. These are cyber physical systems that do a variety of things that you see here, from HVAC control, thermal comfort, electricity supply, fire and seismic safety, etc. So the new opportunity that comes into the picture here with these new kinds of devices that people bring in, that people bring into their offices, is first, you have these new devices that many of them may be plug load kind of devices. So you're mixing this kind of building data coming from traditional building management systems, from Siemens, from Honeywell, from Johnson Controls, with individual centric data. And if I can combine this, then there's a whole host of possibilities that open up. And that's what we tried to explore within the Tippers project. So we have this instrumented building. It's a 6-story building, lots of faculty offices, research labs, lecture halls, like everything else that many of you are familiar with and live in. It's in a living lab on a day-to-day basis. So we installed a variety of sensors, including audio visual, people counters, a lot of Bluetooth beacons, and here are some examples of different, Wemo power monitors, and this was, over the years. These are physical sensors that are instrumented. We also got data from our campus folks, facilities folks, things like HVAC and lighting information. So the idea is these are sensors. There's lots of them, and this was a very old picture, but what are we transforming that to? We want to take this data and transform it into semantic information that people recognize. How much energy is being used in this room for a particular meeting? How many people are in this building at this point in time? Very useful, for example, if there's a fire in the building and the fire department wants to know who's located where. Or maybe if you want to know, is there a portion of the building that's not being used? So this idea of taking these streaming data coming from all of these different devices and creating, think of it as a database table. It's populating and analyzing and populating these higher level semantic information about energy usage, about presence of people, about occupancy, about a variety of other interactions. And we built a bunch of applications, in this using just these variety of sensors. Here are some examples. Concierge, a smart building application. You walk into the building, there's a concierge that shows up that almost like on your phone that says, gives you a map of the building. You're looking for the nearest restroom. You're looking for how to get to the meeting that you're going to, for example. That's what the concierge does. A smart meeting, Noodle was a sort of a smart meeting variant of Doodle. Essentially, how many times have you gone to a meeting and people haven't shown up? So this gives you a sense of, where people are. Are they showing up? Are they in the building? Are they close by? How many people are at the meeting, etc. And of course, we developed some analytics applications for the facilities managers that kind of tell them, information about how much energy is being used in different places versus occupancy. Applications for smart thermal comfort, and yesterday we heard quite a bit about that. And also some other interesting applications that we got out of hackathons that students developed. One was a smart recycling project that came out of a group that actually is still very active today called Zotbins. aiming to make our campus zero waste campus, a zero waste campus. And there was another one which for you could, without any other instrument, you could kind of figure out who are you with, how much time are you spending with people, which kind of spaces are you occupying more frequently, a self-awareness app. Now, all of this is, of course, very interesting, but there are risks. The risk is the more devices we have, the more the security risks. And I really want to distinguish between security and privacy here. So more devices, bigger the attack surface, more the possibilities for vulnerabilities and exposure and release and improper use of that information. Privacy is a sort of different issue. These are highly granular sensors that might be capturing information for whatever purpose, but even if they're capturing applications for an application, they may reveal intentionally or unintentionally information about people's habits. For example, somebody disappears every 2 hours out of the building. Maybe they're smokers. Maybe that's not something everybody wants to know, or you want everybody to know. You may provide information about who you're with most of the time, things that people consider private. And we ran a really simple experiment. You don't need to have an app. You just come into your building with your Wi-Fi connected device, and just by the connectivity and disconnectivity events, we are able to predict what's happening in the building. Okay, what's when people arrive, when people leave. And you may say, this sounds fairly innocuous, nothing really. We're able to run some very simple classifiers on this data and be able to distinguish between who's a visitor, who's faculty, who's staff, with reasonable accuracy. Okay, and we are even able to find out if there are social groups in certain spaces based on co-occurrence of certain types of individuals in certain spaces. There's always a student meeting at this point on this floor, and there are 7 or 8 people, for example. But you could also combine this with other information to get more, intrusive information. Average time faculty spends in the office. If I know your schedule of teaching, I can usually find out, and I know where your office is. I might be able to find out, are you always late to your classes? How tardy are faculty? And many, sounds interesting and funny, but it could be potentially misused in different ways, right? And there's lots of other types of inferences. So even if the data wasn't direct, by processing this data, a lot of video data will say, hey, I'm going to obfuscate. But if I see this obfuscated person coming out of this office, going into here, going into another lab, I can have a good guess as to who it is, right? And so these kinds of inferences that can be obtained from information is really a privacy challenge. And one of the Stippers projects tries to do is to bring privacy by design at the get-go when you design applications, when you design the system. And we have a variety of smaller technologies that we've developed that incorporates principles such as, multi-party secret sharing, privacy policy-based privacy enforcement, where you can state policies as to who can see your information, where, when, and for what purpose, and a differential privacy. Today, with regulations such as the European GDPR, the California CCPR, this is really a huge issue. And over the years, we have developed, as I said, several applications and deployed this technology in multiple places, including a Navy destroyer, where you would think privacy is not an issue, but believe me, privacy is a big issue because people get very little private time in these kinds of settings. And to sort of shift gears a little bit, let's assume now we have the smart space, we have all of these smart apps, and now we have this IoT-enabled building, or the Bren Hall building that I have with all of these sensors, and there are a variety of occupants. Now let's assume there's a fire in the building, right? One would think typically, somebody calls 911, a fire department comes in, an incident command post is set up, and firefighters are coming into the building. One would imagine that if you had a smart building, shouldn't you be able to use all that data to help on the fly, pass that information on to firefighters when that information becomes available so that they can get better situation awareness? Shouldn't the incident commander be able to see where there are people? Should they be able to access the Wi-Fi network and the sensors that are in the space in a seamless manner? And that's something what we aim to do. It's a challenge because you have different data sources, different people wanting information. You have a constrained network, because of the fire. Maybe some part of it doesn't work anymore. And so, how do we exchange this kind of heterogeneous information in a prioritized manner to different stakeholders in time as the network evolves, as the situation evolves? It's not a static situation. It's not like that's how it is. The fire is changing, it's moving. And so this was sort of one of the projects that we did. And I will not talk a lot more about it because I'm seeing lots of hearts on my screen. We also extended this to address high-rise buildings. High-rise buildings are very interesting because when fires happen in high-rise buildings, there are special things such as the stack effect, which causes this fire to spread and the impact of the fire. There are these exterior wall assemblies that are especially used today in sustainable buildings that essentially catch fire a lot more easily and spread fire on the exterior of the building. And so and if there is, for example, any open doors or windows, that can completely change the fire spread models and the ventilation status of these buildings. So one of the things that we're doing is combining these model-driven based approaches with data-driven approaches. We want to be able to detect how the fire spread. We want to be able to detect if windows and doors are open. We want to be able to detect humans if they're trying to escape. And long story short, we're attempting to use drones to be able to capture images and analyze these images to assess these situations. So I won't talk about some of the other COVID applications, but I'll give a quick 1 minute.
I'm so sorry.
Introduction to this new project on disaster resilience for aging communities. And this was something that struck me really hard on several of us. This was a picture from a nursing home in Hurricane Harvey. And if you notice, here are residents in a senior home sitting waist deep in water, knitting. And this picture and any time when disaster strikes, independent of the disaster, independent of the location, the elderly are the ones that suffer the most, not because of the disaster alone, but because there is not enough information available about how to triage and keep them safe during that whole disaster. And that's what our goal was, to get information preparedness to the responders, to the caregivers, to people who are being evacuated. Think of it as the older adult can carry information along with them. And what we did was we're trying to create this digital twin that in a fire event gives the responders better information about older adults, their needs, so that if they need dialysis and they need to be moved to a facility with dialysis, if they are oxygen dependent and they need to go to a place where there is power, don't evacuate them to a high school building. Where you might get out of power. And so these kinds of situations, information preparedness being created for the purpose of keeping older adults safe is what the civic engagement or civic innovation project is about. And
thank you.
I leave us with this slide. There's a lot of partners and challenges here, and
thank you,
a very interesting challenge for us.
I'm so sorry.
That's all right. I always have more slides.
I know we want to at least ask one question before we go into the breakout. Burton, our moderator, could you pick a question?
Nalini, thank you so much for this talk. And you touched on privacy and security issues, and there are a number of questions actually in your speaker page, which would be great if you can go and comment. As well as in yesterday's discussion. So I will ask a different question. So there's this question related to real-time decision-making with all of these data, multimodal data coming from multiple sensors and multiple locations about multiple tasks. Mm-hmm. So how real-time are some of these things you're talking about, and what is the time delay?
Yeah, so of course, in many of the, it depends on the kind of setting. So if there's, a disaster setting is very different. where you might actually need people to go and ferry the data or drones to go ferry the data, which means inherently there's delay tolerance. Usually, for a lot of these monitoring kinds of applications, it's close to real time. So right now we have an active dashboard using our tippers framework that allows people to get, occupancy of rooms to understand social distancing in the context of COVID, right? And it's pretty live. I would say, seconds. But on the other hand, there's also a scalability issue. So the architecture, the data architecture, that is critical, because how do you design scalable data architectures? If I bring privacy into the picture, that actually changes the scalability solutions quite a bit, because if each person has 20 policies and there are, 2,000 people on campus at the same time, every time a data gets collected, it has to be matched against these policies. That can cause delays. And so part of what you're saying is very true. How real time can it be in a scalable manner is if it's just one building, what's happening in a room, like, we have a pilot facility at the senior home, may not be that hard. But on the other hand, if I start putting a lot of policies in and putting a lot of high bandwidth sensors that need to be interpreted, right? If you're only interpreting small Wi-Fi data, maybe a little less challenging than if I have to do video analytics. And so the answers, sort of roundabout answer to your question is it depends on what you're trying to do and how accurate you want. In fact, one of the areas of research, and I kind of glossed over it, is something that we call progressive sensing and decision making. So you get some kind of abstract decision, which is rough. So you get, maybe there are somewhere between 10 and 30 people in this room. And as time goes by, and if it is essential, you can refine that more with more granular data. So you use low cost data to get an approximate view of the situation fast. And you can use sort of more intrusive sensors or more data to get a more accurate picture. And this is something we're doing with progressive data management. In fact, we're calling this progressive enrichment kind of database we're building is called EnrichDB.